Well, so in the first problem, first we have the Newton's law of cooling or heating, and we have to put together dt and t minus ta to then when we can be able to integrate it, making it with u substitution, we can put together constant c and constant 2 because they both are constant. And then to get rid of the natural logarithm, we need to use an exponential, and we only then have to solve for t, and we have a function of temperature with respect to time. Then to the interpretation of the constant c, we have to evaluate our mathematical model previously mentioned to at t0. Then we only get T0 is equal to C plus T8, and we solve for C. We get that C is the difference between the initial temperature and the ambient temperature. And here in the graph, we can see that in our mathematical model, when we have cooling process, the C will be positive, and when we have a heating process, the C will be negative. For the application to an aluminum rod, we have to evaluate T0 in our mathematical model and substitute the values that were given in the problem. And then we can only solve for C, which it gives us minus 260. Then we can update our mathematical model and evaluate at another data point for us to be able to get the K. For this, we need to use natural logarithm to get rid of the exponential, and then it is when we can solve for k and get the value. And another update to our mathematical model now with the value of c and k in it, and then we can solve the problem of how long it takes to the road to cool down to 26 Celsius degrees. Um, it's the same. We have to get the t, so we put all our values previously obtained, and then we have to get rid of the exponential, making use of natural logarithm. Then we have to solve for t, and the t gives us 3251.86 seconds. Then we have our MATLAB simulation, which is an analytical solution. First, we put our experimental data and our time vector. Um, these values, then we use it to get the C and to make our mathematical model. And then we only have to graph it, and this is the graph that give us. Then we have to use, again, a MATLAB simulation, but with Euler's method. We also have to put our experimental data, our analytical model, and then we have to use an approximation Euler's method. So we have to make a new vectors and a new process. This is an Euler's approximation method process, which give us this graph, which is very, very close to the analytical model. Then in problem two, what we have is the heat transfer equation, and we have to introduce time to this equation to find an expression for temperature over time. So we multiply 1 over t in both sides of this equation. Then we get that heat over time is equal to power, so we can substitute this. Um, Now that we have only time on one side of this equation, we can solve for final temperature, which give us our new mathematical model, which is power over mass and specific heat capacity. This is multiplied by time plus the initial temperature. So then for the next problem, we have a high power heater. which has 1000 watts, which is put into a container with zero point 0.8 liters of seawater, and we need to obtain a graph of temperature with respect to time. So we have to put first our experimental data, uh, and I need to say to search for the specific heat of seawater. Then we have to create the vector of time and put it all values on our mathematical model that we previously saw and graph it. And this is the graph of temperature in respect to time of this problem. And the next code performs a fifth degree polynomial fit to experimental temperature data over time. First, it generates the time vector and constructs the designed matrix with powers of t. Then it solves the least square systems, x a is equal to y to determine the polynomial coefficients. And finally, it evaluates the fitted model and plots the resulting curve, allowing visualization of the temperature trend over time. This is the graph. For the problem 3, we are given some values of thermal equilibrium of water and copper. And we have to apply the principle of conservation of energy, the calorimetry principle. So then we substitute our given values of each material. And delta of T is the same, the final temperature for both materials, since when they reach thermal equilibrium, they both are going to share the same temperature final. And then we have to group similar terms and solve for T final, temperature final, or final thermal equilibrium. And then we have our mathematical expression to determine final equilibrium and temperature thermal equilibrium. To calculate the final temperature of both materials, we substitute our given values on our mathematical expression, and it gives us a final temperature of 48.10 Celsius degrees. For the fourth problem, we have a right circular cone made of steel that initially has a volume of V0, and we have to prove that the object will experience a volumetric thermal expansion after a delta of T. First, we have the volumetric thermal expansion, which is given by delta of volume is equal to initial volume times delta of temperature times the volumetric thermal expansion coefficient. Uh, Here in the image, we can see that at first the volume has a height of h0 and a radius of r0. Then it experiences a I'm sorry, delta of temperature, and then the new height is h0 plus delta of height, and the new radius is r0 plus delta of radius. We can see on the bottom of each cone its respective volume formulas, and then we got that the delta of volume is given by volume minus initial volume, which we have um, both of them here. We only substitute them in this equation. Then we have to group similar terms. Um, we have to multiplicate all this by p over 3. Then we have to expand it. We expand it all, as you can see here, and then we can um, cancel some terms because they are very small values or they are neglectables. Um, What remains is this, and we can substitute delta of R and delta of H with these values of here. Then we can also group some terms. We know that these are two similar terms, so we can add it together. Then at the beginning, we were obtaining this formula of initial volume, which it repeats right here. So we can only substitute, and then we are given this equation, which this represents that the object will experience a volumetric thermal expansion. So now for the calculation of the thermal expansion, we have our experimental data, which is given to us in the problem. And we only have to substitute the values and we get the thermal expansion, which is this. And now we have to look for the final volume. So in this equation, we only solve for final volume and again substitute our values and the final volume is given by this, which is 10.59 um, 45 liters. And in the final problem, we have to use the ideal gas equation and solve for T. And for this problem, we know that the R and N are constants. So both pressure and volume increase from the point A from the point B, as we can see in the graph. So we can assume that temperature will also increase as the product between P and B, pressure and volume will also increase. Mhm. For this, we know that the temperature in B will be greater than the temperature in A. As volume and pressure increase, the temperature must also increase according to the ideal gas law. For the next problem, we need to get the work done by the gas, assuming it behaves as an ideal gas. So we are given the volume and pressure at A and also at B, as we can see here in the graph. And for getting the work, we need to get the area of this. First, we have a rectangle, and on top we have a triangle. And since it is a pressure volume diagram, well, the work is simple as the area of that. So here we have base times height over 2. We substitute our value, and it gives us 800 joules. And then for the rectangle, we have base times height, and substitute our values, which it gives us 4,000 joules. At least we only have to add them together for the total area of this PV diagram, which it gives us that the work is 4,800 joules.